Hey, welcome back, everyone. Today we are going to dive into chapter 7 and we are covering sampling distributions. So stick around and we're going to go through that. We're going to do some examples. So all of that will help you with this chapter. All right, so the objectives for this chapter is to understand the concept of sampling distribution. So we're going to see what the sampling distribution is all about. At the end of this chapter, you should be able to compute probabilities related to the sample mean and the sample proportion. So we'll talk about the difference between the sample mean and the sample proportion. Uh, and we're going to go over some examples, so that should help you also with the homework. And finally, we're going to talk about the importance of the central limit theorem, and we'll see what that's all about. Okay, so what is sampling distribution? Basically, a sampling distribution is the distribution of the results if you actually selected all possible samples. So your main concern when making a statistical inference is reaching conclusions about the population, not the sample, right? The sample mean is unbiased because the mean of all the possible samples means is equal to the population mean. So what are we talking about here? So imagine that you like swimming and you have a medium-sized pool, let's say 25,000 gallons. And one of the things that you need to do is you need to keep your pool clean, so you want to go swimming in it. Uh, One of the things to keep your pool clean means you have to put chlorine on it. Chlorine gets rid of the bacteria and keeps the water clean. So how do you know how much chlorine to put in? You have to measure what the pH for the pool is. So imagine if you had to measure every single gallon on that pool to figure out what the pH is, so you can know how much chlorine to put in your pool. That's 25,000 gallons. So you have to measure each one of those. That will take you a long time. By the time you're done, it'll be really difficult to begin with. Instead, what most people do, they grab a little piece of water, not even a gallon, they just grab a little bit of water and they measure the pH. Then they go maybe to a different part of the pool and they take a different sample and they kind of get an idea what the pH is, and they use that uh, to figure out how much chlorine they need to put in the water. So again, the importance of getting a sample is that you don't have to measure the entire pool. Now, the sample from one part of the pool is going to vary from the sample on a different part of the pool. So if you got water from the top, it's going to have a different pH than if you grab water from the bottom of the pool. And the reason is that the chlorine evaporates. So the water at the top is going to have less chlorine because the sun is beating on it and the chlorine is evaporating. Uh, Bottom line is that each gallon is going to have a different pH. But if you were to test each gallon and then you will get the mean of each gallon, it will equal to the mean of everything that is on the pool. That just makes sense, right? Because the pool is composed of every single gallon of water that is on the pool. And that's why we mean that it's unbiased. Because if you were to take each sample, each gallon, and you were to get the mean of each gallon, will equal to the mean of the pool. Okay, so here's an example of why we say that the sampling distribution is the sampling distribution uh, has the normal is equal to the normal distribution, and this is what we mean, right? So we're going to do a very simple example. Let's say you have a population of 4 people, okay, and then you're trying to figure out what the age of each individual on this population is. So you take 4 people and their age are 18, 20, 22, and 24. So this is your population, these 4 people. And if you were to get a measure of the entire population, you will have that the means of all of those is 21, right? You have 18 plus 20 plus 22 plus 24, and then you divide it by 4, you get your mean, and that equals 21. Here is your standard deviation, right? That is the sum of all of those, and the standard deviation equals 2.236. Now, do you see how this is a uniform distribution? So this is a uniform distribution. It's not a normal distribution. Remember we talked about those type of distributions a few chapters ago. So here you have a uniform distribution. Now let's assume that you want to select a sample. And on this case, we're going to make it really simple. You're going to take a sample of 2, right? So this, we're assuming that the sample is done with replacement. So if you select a sample of 2 individuals with replacement from this population, there are 16 possible samples. And you can see here, right? You grab the first person and it's 18 years old. You put the back on the pool and you could grab the person again. So it's 18 years old again. So here's the first observation. You can grab each one of those 4 people. And on your second observation, you can grab any one of those 4 people again. So here it is, right? And then you get the means of your samples. So you, on the first observation, you get 18 and 18. And so these will give you 2 18s, right? And then you have your mean will be 18. So let's say you get on your first observation, you get the 20-year-old. And on the second observation, you get the 18-year-old. Then your mean is going to be 19, and so on and so forth. So now that we have all of that data there, that you picked at 2 possible observations, let's see what happens. And now, once we get the sample means, you see how this look more like a normal distribution. It no longer looks like this uniform distribution, but now it looks like a normal distribution, because there is only one way to get a mean of 18, and that's if you pick at the same person twice. There is 2 ways to get a mean of 19, and that is if you pick at a 20 and at 18, or at 18 and at 20. So that's why the 19 is there 2 times. There is 3 ways you can get the mean of 20. That is, mean if you, in your first observation, you pick at somebody who's 22 years old and somebody who's 18 years old. But you can also get a mean of 20 if you pick at the first person you pick is a 20-year-old, and then you pick the same person again, so you can get that 20 again. Or if you pick that 18-year-old, and then you pick a 22-year-old, you get the mean of 20. And that's what these numbers represent. So once again, here you can see this is a uniform distribution. I'm sorry, this is the bell shape, the normal distribution. It's not the uniform distribution. Okay, so what we're doing here, right? We're measuring measuring of the sample distributions. So if you take all of those means, right, and you divide it by 16, which is all the samples that you have, you will get that you get a mean of 21. So go back in here, and you saw that your mean was 21. Now, once you get the means of all your means, then you get a mean of 21 once again. Now your standard deviation changes. Now your standard deviation is 1.58, and the reason is we're dividing by 16, right? Because we have 16 different samples. Okay, so here is your population. You have your mean of 21, and you have a standard deviation of 2.236. Once you do the sample means, so you take sample, you get the mean. Your mean stays the same. See how that mean is 21, this mean is 21. The standard deviation will change because you're dividing by a different number. Right now you're dividing by 16, and your standard deviation is 1.58. So the value of the standard deviation of all possible means, we call that the standard error of the mean, and express how the sample means vary from sample to sample. So the standard error of the mean is equal to the standard deviation of the population divided by the square root of the sample size. So going back to the pool example that we talked about, it, right? How much does the mean of the first gallon of water that is towards the toward the top of the pool, how much different is that from the actual mean of the entire pool if you were to measure all the 25,000 gallons? So there is going to be a little bit of variance, a little bit of difference between those means, and that's what we call the standard error. So as you guys can see here, you have your standard deviation, and to get the standard error, you're going to take the standard deviation and you're going to divide it by the square root of the sample size. So the more samples you get, the more accurate the number is going to be. So basically, once the standard error of the mean decreases, as the sample size increases, so basically the error is getting smaller and smaller. So if you were to start measuring those 25,000 gallons, and the more that you measure, the less the error is going to be, because you know you're getting closer to the actual mean for the pool. So if you're sampling from a population that is normally distributed, then or regardless of the sample size, the sampling distribution of the mean is normally distributed. Basically, on the sample that we saw with people having different ages from 18 to 22, we saw we saw that distribution was not normal. But if the population is normally distributed, all you have to do is get one sample and you will get a normally distributed mean, because the population is normally distributed. So again, if a population is normal with a mean of mu, and the standard deviation is the standard deviation, then the sample distribution is also going to be normally distributed, and you can see that in here. So you have the mean here is going to equal this mean, and also your standard deviation is going to be equal to the standard deviation divided by the square root of the sample size. Here we're talking about the C values, right? Remember, we have the normal distribution, and one of the things that you're going to have to do is going to be able to transfer those X values into Z values. So here is the Z value of the sample distribution, and the formula is the same as we've been using. Obviously, we're going to have to use different values for the sample distribution, but here you see that X bar is the sample mean, and then you have your population mean, you have your standard population standard deviation, and then you're going to have your sample size. So, but the formula to transfer X values into Z values is pretty much the same. You subtract your population mean from the sample mean, and then you divide that by the standard deviation divided by the square root of your sample size. And this is what we mean here. Here is your normal distribution curve, right? This is the bell-shaped curve. And here is your mean. Here are your X values, right? So here will be the normal distribution, and it has the same mean. As you guys can see, the mean is the same. So the mean of X bar, or your sample, is going to be equals to the mean of the population. And one thing that we mentioned is that X bar is unbiased, because once you add all of those means, it should equal to the mean of the entire population. That's what we mean when we say that it's unbiased. So as you get more, a sample size gets bigger, your mean is going to, your standard deviation is going to be smaller. So it makes sense, because now you are dividing by a bigger number, so it's getting smaller. As you guys can see here, the blue line represents the smaller sample size, but as you are dividing by a larger number, this standard deviation is going to be smaller. The mean is going to stay the same, but the standard deviation is going to get smaller. So you get this red line here, and you guys can see how that is much larger based on the sample size. So that means the standard deviation is getting smaller, so the values are getting close together. Okay, so let's do our first example. It says find a symmetrical distributed interval around mu that will include 95% of the sample size when mu equals 365, standard deviation equals 15, and your sample size is 25. So what we're gonna do is let me get out of this presentation, and what we're gonna do is actually gonna put that into a Word document, because it'll be much easier to explain. Okay, so here we have our standard normal distribution, right? So what we're trying to do is we're trying to find 95% of the values. Here's our problem. So we are trying to find 95% of the values, The mean is 368. The standard deviation is 15. Our sample size is 25. So first thing we need to do is, right, we need to realize that this is symmetrical. So we can use the subtract 95 minus 5, and that'll give us 5%. And then 5%, so we have 5% on each side. So we have to divide the 5% by 2. So that'll give us 2.5. Basically, what we're trying to do here is we are trying to find 95% of the values. So we're trying to find 95% of our values. And what we're going to have to do for this is we are going to have to open our C table, right? So where is 95% of the values, right? We don't know. So what we're going to have to do is find where those 95% of the values are. Okay. So what we're going to have to do is we're going to have to use our C table. So here is our C table. Let's find the 95%, the 5% of the values, right? So 5% is the part that we don't need, right? So we have 95%. Remember, from here to here is 100%. So 100 minus 95, that'll give us 5%. And now, because it's symmetrical, that means we have half in one way and half in the other. So that'll give us 5% divided by 2. That'll give us 2.5%. So we need to find the 2.5%. So I'm going to go here to my C table, and we need to find 2.5%. And 2.5% is going to be right here, 0.025. That's 2.5%. So it's 1.96, right? Here is the 6, and it was right over here. So it's negative 1.96. We could also use the rule that says that 95% of the values are between 1.96 standard deviations. So more or less, I think we were close here, is that we are, we are right over here close to the -2, because we know this curve is symmetrical. So this is also going to be right over here. So this is our answer here, is 1.96 standard deviations from the mean. Does that look like a 9? Probably not. So negative 1.96 and negative 1.96. Okay? So that is our answer. All right, let's get back to our presentation here, our PowerPoint. So here it is, right? Since the interval contains 95% of the sample means, 5% of the sample means will be outside of the interval. That's what we talk about it, right? We know it's symmetrical, so each size contains 2.5% or 0.025. And then all we have to do is find the C-score, which we did on the table, and we saw that is 1.96. Actually, before I move on, let me show you one more thing. To find the other 2.5%, right? We need to, where did I put this thing? Okay, so we need to find the other 2.5% here. If you want to use this, if you find this one on that side, you already know you got it right. But let's say you want to double check, and you want to grab the C table. Let me get back to my C table. Where is my C table here? So the other the other to find the other one, you will have to go here and you will have to do some calculation. Let me use my calculator just to show you what I'm talking about here, right? So you have 1 minus 0.975, and that'll give you your 0.025. So you need to find, oh, I'm sorry, 1 minus 0.02025. So we need to find a 0.975 to be to the left. So you will go here, and again is right over here, which is 1.96. Right over here, 1.96. And that's how we get the 1.96 here, but we already knew that because we know it's symmetrical. So if you find one side, you are definitely also finding the other side here. Let me see, where's my eraser here? Gosh, sorry about that, guys. My eraser didn't work. Okay, so let's move on. Okay, so that's how we find the z-score, and that will be the answer to that one. Now, we need to calculate the lower limit of the interval. So to do that, we have here that x bar, the lower limit, is going to equals to the mean plus the z-score times the standard deviation divided by the sample size. So let's go back to my Word document, and we're gonna do this over here. Let's see what this is talking about here. So if you read your textbook, you had this problem right from the beginning. It said that if the serial lines manager for Oxford Cereal Plants number 3, you are part of the project team overseeing the installation of 3 new field production lines. By automating the bag information, field bag sealing, and weighting operations, 3 identical lines running at plant number 1 have increased the production of boxes of flake cereals on that plant by 20%, and similar gains are expected at plant number 3. In the future, these lines will give Oxford Cereals management greater production flexibility by allowing the option to use packaging other than the standard pillow bags long use. Okay, so let's go back to what the problems actually says. For now, you must verify the calibration of plant number 3 by field production machines. Proper calibration should ensure the field boxes will contain a mean of 368 grams of cereal among other attributes. If the calibration is imperfect, the mean weight of the boxes could vary too much from the 368 grams claimed to be on the pre-printed boxes used in the lines. You decide to take samples of these cereal boxes being produced on the initial runs of the new line. For each sample of the cereal boxes you select, you plan to weigh each box in the sample of the calculated sample means. You need to determine the probability that such a sample mean could have been randomly selected from a population whose mean is 368 grams. Based on your analysis, you will have to decide whether to maintain, alter, or shut down the cereal filling process. Okay, so that was a lot, but basically what we're trying to say here is you want to find out with a 95% accuracy to see if those boxes have 368 grams, if their mean is 365, right? So here it is. The packaging equipment that is filling 368 grams boxes of cereal is set to that amount of cereal in a box is normally distributed, right? Which a mean of 368 grams. The standard deviation is 15 grams. So basically you need to find an interval symmetrically distributed around the population mean that will include 95% of the sample means based on sample of 25 boxes. So here is our formula to convert the formula for finding the x for the sample distribution of the mean. So once we do that, we can go back in here, and all we have to do is add those values. So our mean is 368. That is giving us by the problem here, right? So we do have 368. Oh, well, let's type in there the lower limit. This is going to equals 368 minus our z-score, right? Plus our z-score. We already know our z-score is negative 1.96. We did find that out, right? 95%. Remember how we just find that out in the prior slide. So we know our z-score is 1.95, and then we're going to multiply that by our standard deviation, which tells us in here it's 15 grams, divided by the square root of the sample size, and the sample size is 25. We know the square root of 25 is 5, so we're just going to write 5 in there. Okay, so 15 divided by 5 times 1.96, and let's see here. All right, so here it is, 15 divided by 5 equals 3, right? And then multiply that by 1.96, and that'll give us 5.88. Remember, this is negative, right? Negative 5.88. So this will equals 368 minus 5.88. And once we do the subtraction, we get that our total is 362.12. And that will be a lower limit. Now we need to calculate the upper limit, which is going to equals 368 plus, in this case we have a positive 196. Remember we did that on the prior slide, times 15 divided by 5, and that is going to equals 368 plus 5.88, and this is going to equals, let me see, 5 plus 68, that is 373.88. All right, and this will be our upper limit and our lower limit. So let me just go back in here, and this is what we're talking about here, this area right over here. Okay. All right, so based on the sample size of 25, the sample means in 95% of all the samples are between 362.12 and 373.88. All right, so let's talk about the sample mean for the sample distribution if the population is not normal. So in the prior example, the population was normally distributed, so it doesn't matter what the sample size. We know the mean was going to be a normally distributed. So what happens if the population is not normally distributed, right? So we can use the central limit theorem. So if you read your textbook, you know that the central limit theorem says that the sample distribution of the sample means approaches a normal distribution as the sample size gets larger, no matter what the shape of the population distribution was. So remember a few slides ago, we saw a population that was not normally distributed, but once we get the means, we got a normal distribution when we were looking at the different edges. So that's based on that's what the central limit theorem says. Even if the population is not normally distributed, if the sample size is large enough, then the means are going to be normally distributed. So just one thing you need to know is that the mean of the sample is going to equal the mean of the population, and the standard deviation is going to be this, the standard deviation divided by the square root of the sample size. So let's take a look at this picture here to help us explain something. So this, you see this blue line here, that's not normally distributed, right? You guys can see it's not normally distributed. But the mean, which is the red line here, will be normally distributed if the sample size is large enough. So one thing that you may be asking is like, what does that mean, large enough? So we can say as long as you're getting a sample size higher than 30, then you can pretty much be assured that it's large enough. So anything about 30 will be large enough to be considered to use for the central limit theorem. So here we have the sample distribution. You have the central tendency, right? Where you have your mean of the sample size is going to equal the mean, so that it's going to be the same as the mean of the population. And then you have your variation where your standard deviation of the sample size is going to equal the standard deviation divided by the square root of the sample size. So remember, the larger that it gets, right, the more this is going to look like a normal distribution. So the larger that your sample size is, the more that this is going to look like a normal distribution rather than looking at any other type of distribution. So here it is, how large is large enough. So for most distribution, when you have a sample size of 30, we'll consider that is large enough to give you a nearly normal distribution. If it's fairly symmetrical, you only need 15 to be considered large enough. And remember what we talked about it, right? For a normal population distribution, the sample distribution of the mean is always normally distributed. So if the population is normally distributed, obviously the sample size is the sampling distribution will be normally distributed. All right, we're going to do one more example. Here it says that you have a population that has a mean of mu is equals 8, and the standard deviation is 3. So suppose a random sample size of n equals 36 is needed, right? Because on this case, we don't know if the population is normally distributed, so we want to get a sample size higher than 35. I'm sorry, higher than 30 so we can apply the central limit theorem. So what is the probability that the sample mean is between 7.8 and 8.2? And here is our solution, right? So in this case, it doesn't matter if the population is not normally distributed. The central limit theorem can be used because our sample size is bigger than 30. So the sample size of the distribution of x bar, which is your sample size, is going to be pretty much normally distributed. You have the mean equals to 8, and your standard deviation is going to equals the standard deviation of the sample size of the sample divided by the square root of the sample size. On this case, the problem was telling us that our mean is standard deviation is 3, so a square root of 36 is 6. Once you divide 3 divided by 6, that is equal to 0.5. So all we have to do is follow this example here. You have 7.8, right? This is what it's asking us. 7.8, right? Between 7.8 and 8.2. So we need to do 7.8 minus 8, and then you divide that by 0.5, which we know is 3 divided by 36 is 0.5. And on the other hand, you have 8.2 minus 8 divided by 0.5. Now, take a look at this number here, right? We are talking about that C is less than 0.4. So once you get all of these, you get negative 0.4 and 0.4. So basically what we're saying is that we don't know if the population is distributed normal or not, but it does not matter because our sample is big enough. But we have here 7.8, and that's 0.4 standard, negative 0.4 standard deviation the mean is to the left, and 0.4 standard deviations to the right. So this is our population here. This is what we're trying to get. So let me get our C table to show you where those values are coming from. Okay, so here is our C table, right? And we are saying we want the values, we are interested in the values that are to the left of 0.4, right? Here is our 0.4. So these are the values that we are interested to the left of 0.4. Okay, so what we're going to do here is we're going to find 0.4, and 0.4 is right over here, 0.6554. Okay, so 0.554 is this value here. But that includes all of the values, including this little tail here that we're not interested. But we know that is also negative 0.4 standard deviations. So what we're going to have to do is we are going to have to subtract that. We're going to have to remove it. So we're going to have to find negative 0.4, and negative 0.4 is right here, and it's 0.3446. That's where you get this 0.0446. So you subtract 0.6554 minus 0.3446, and that'll give you 0.3108. Again, let me explain why we are removing the 0.3446, right? When we look at our C table, we find that values to the left of 0.4 equals to 0.6554, but that includes everything. Now, this part right here, remember, we're not interested on that part, right? That was this negative 0.4, that's 7.8 minus 4. That is this 4, so we need to subtract that. When we find it, we use the C table to find where negative 0.4 was. Then we can subtract that, and that'll give us 0.3108. Okay, I really hope that makes sense. If it doesn't, make sure you reach out to me. Let me know if that doesn't make sense to you. Okay, so let's finish up with populations proportion, right? So imagine that you are at TMCC, and then you're trying to figure out, how many students have blue eye color. So you will take a proportion of the population because you don't want to look at 12,000 students. So you just grab a population, and then you're trying to figure out how many of those are going to have blue eyes, so you can estimate what the population have. So in this case, you have the number of items, in this case is blue eyes, and then you're going to divide it by the sample size. So here is you have 0 is going to be less or equals to the proportion, which is going to be less or equals to 1. And then you have the proportion is approximately distributed as a normal distribution when n is large enough, right? So we already talked about that. If your n is large enough, it's going to be normally distributed. We saw the bell shape. So let's take a look at this. This is what we mean, right? So you see how this gets normally distributed? That's what we mean. Every time that if the population is large enough, you can assume that the proportion is normally distributed. So here is your standardized P to a C values. Here is the formula. Is the same formula we've been using before. We're just using different symbols. So you have P minus pi divided by the standard deviation of the population, which, looking at this example, you see that the standard deviation of the population is going to equals P times 1 minus P divided by the sample size. So that's what this. I know this might look like it's a lot of numbers in there, but it's just the same number here. So you can see that the mean is going to equals to pi, and the standard deviation, we have the formula there. So here, let's do this one example to look at it. So if the true proportion of boarders who supports proposition A equals to pi equals 0.4. What is the probability that a sample size of 200 yields a sample proportion between 0.40 and 0.45? Just once again, just want to remind you guys that you really don't care about the proportion, right? What you really want to find out is the value of the entire population. Again, when you're taking the sampling for the pool, you really don't care what the pH of the piece of the part of the water that you grab. You really want to get the pH of the entire pool. So again, on this case, right, you are trying to figure out, okay, how many people is going to support this proposition, right? So you can do more campaign, put more money into your campaign to promote a proposition A. So what you do is, because you don't want to sample the entire population, that will take too much money, you just grab a proportion to sample, and then you're trying to figure out what is the probability that with a sample size of 200, you are going to get a proportion between 0.40 and 0.45. So here you have that your pi equals 0, your p equals 0.4, and your sample size is 200. So what is the probability that is going to be 0.4 is going to be equal or less than your proportion, and your proportion is going to be equal or less than 0.45. So if pi equals 0.4 and the sample size 200, here is our problem again. And then first thing we need to do is we need to find the standard deviation. So we replace all of those numbers for the values here, 0.4 times 1 minus 0.4, and then you divide that by 200. You get that it's going to equal to 0.03464. Once you do that, you can convert to the standardized normal, the C table, right? The C values, now that you find those. And here it is, 0.40 minus 0.40, that is going to equal 0. And then you divide that by 0.003464. And so every time you divide 0 by a number, you know you're going to get 0. That's where this is coming from. And on this other end, you have 0.45 minus 0.40. So that's going to equal 0.05. And you divide that by 0.03464. And then you get 1.44. So now that you find those values, then you can use your C table to find your sampling distribution. So on one end you have 0. So we already know that that is where the mean is, right? We know that because it is a normal distribution. And then here is 0.45. And then you move that to the standard distribution. And that's where you get this area here, which is 0.4251. So we can take a look at the C table, and you can find the value here. Let's just do that one more time, just to show you guys where that is on your C table. So we are looking for 1.44, right? 1.44. And that will be right over here is 0.9251, but remember 0.9251, right? So this part to the left here is 0.9251, but we have to subtract the 0, which we know 0 is always a 0.500. So we subtract that, and that will give us the 0.4251. So here it is, right? So 1.44 is a 0.2951. We subtract the 0 because we don't want that part of the data. So once we do it, we get 0.4251. Okay, guys, I really hope that helps. If it doesn't, shoot me an email, let me know, and I can take a look into it, see what can I do to help you or to make things more clear. So to summarize what we talked about today, we discussed the concept of sample distribution. So remember, when you have data, even if it's not normally distributed, if you grab the sample means, those are going to be normally distributed. That's why sampling distribution is very important. That's why the standard uh, table is very important, right? We talk about computing probabilities related to the sample mean and the sample proportion. And remember the central limit theorem, right? As long as the numbers are large enough, those sample means are going to be normally distributed. Okay, guys, that's all I have for tonight. Shoot me an email if you have any questions. I really hope this helps.